you for organizing such a program, and that will help so many students. So to give a foundation. So I think Rajesh has already covered the adjacency matrix and how it's related to graph structure. So I'll go for Laplacian matrices. So for Laplacian matrix, obviously we'll use adjacency matrix, but today's talk is on Laplacian matrix. I hope that you know already what is adjacency matrix. And I'll speak about matrix T theorem. That is one of the important theorem that actually made it happen that we are now targeting or looking for Laplacian matrix and its eigenvalues. So to start with, my outline would be, I'll speak about Laplacian matrix, its properties, and then I'll go for matrix T theorem. Then I'll say some related problems, and then I'll go for references. So yeah, I don't know. Okay. So the screen is coming on my slide. I mean, this
pointer I can see on the slide.
on the slide, anything is coming, those photos or names in the side?
No. Only the
Only
full
slide.
only
Okay.
slide. Yes.
Okay. So here, we are taking a simple graph first, but everything can be generalized. So G is a graph and it's a simple graph. That means I'm not allowing loops or parallel edges, and it's on-directed. Obviously, we'll use the directed graph also, but I'm taking a on-directed one. So it's a simple on-directed graph. Then the Laplacian matrix is defined in this way. It's an n cross n matrix if you have n vertices. And the ith entry, that will be di. If it's like I equal to j, that means all the diagonal entries, that is the degree. So degrees will be on the diagonal, like here you can see the example. And off diagonal entries, those will be like a -1 if I is adjacent to j and 0 otherwise. So given a graph, like this is a example. So here, like you can see 1 and 2 are adjacent. So I'll put a -1. 1 and 2 are adjacent and 2 and 1 also adjacent. So I'll put again -1 there. Like this, it's and if there is no edge, like from 1 to 4, there is no edge, then we'll put 0 accordingly. And diagonal entries are all degrees. You can see the degrees just I put. So this way the matrix is defined. Then you can obviously observe that this matrix is nothing but it's dg minus ag. This way I can express dg, the diagonal matrix with degrees on the main diagonal, and ag is already you know that is the adjacency matrix. So that way also we can write it. So Laplacian matrix is in like some book it's defined in this way: lg equal to dg minus ag. Okay. So in AG, you observe that AG is a symmetric matrix when graph is simple, and it's a non-negative matrix. So like Perron-Frobenius theorem and other things can be used. Here, if you see, the Laplacian matrix is not a non-negative matrix. It contains negative entries, 0, and some other integers, which are the degrees. So this way the matrix is, but it is a symmetric matrix that can be observed. Now I'll speak about another matrix that will be used also to define Laplacian matrix. So that is the incidence matrix. So incidence matrix is vertex as incidence matrix that can be defined for on-directed graph, but here we'll put it orientation to the graph G. So any arbitrary orientation you can give to your original graph G so that it will become directed. And then define this matrix in this way. So QG is like if the graph has n vertices and m edges, then QG will be n cross m. So it's like rows are indexed by the vertices and the columns will be indexed by the edges. And this way the matrix is defined. Its ith entry will be 1. If the edge is that originates at I, and you can put -1 if E is a terminate set I. So, and 0 otherwise. Like in this example, you can see. So I made your original graph as directed. So I put directions to edges, and then like if I am looking for entries. So as I told, the matrix will be like indexed, rows are indexed by the vertices. So this is like 1, 2, 3, 4, the 4 vertices. And then edges are your columns are indexed by the edges. So here E1, E2, E3, E4. So if I look at the entry which corresponds to the vertex 1 edge and edge 1, then edge 1, for edge 1, the starting vertex is 1. So this I'll put 1. And for edge 1, the terminating vertex is 2. So for 2, this I am putting -1. And the other entries will be 0. For each column, you can observe similar way that you will get a +1 and a -1 corresponding to the end vertices. Other entries will be 0. So this is known as the vertex as incidence matrix. And here, because each column contains 1 +1, 1 -1, so column sum, if you look at, that is becoming 0. And if you look at each row contains how many non-zero entries it's containing. That is basically the degree of the corresponding vertex. So like vertex 1, that is like corresponding to row 1, and that contains 2 non-zero entries because degree is 2 basically. So, and 2 edges, they are starting from 1, so 2 plus 1s are coming in this first row. Similarly, if I look at vertex 2, here 2 terminating edges are there. So the row contains 2 negative entries. This way it is. So if I look at the modulus of all entries in each row and add them, that will give me the degrees. And if I add all the columns entries, I'll get 0. So column sums are 0. Now, if I consider this matrix, our Laplacian matrix is nothing but this Q into Q transpose. So that can be observed easily, like in this example, if you see. So when I'm making Q into Q transpose, basically the row, I'll take the first row and then I'll make the inner product with itself. That will give me the first entry in the product. So this, when it will be multiplied with the same row, it's transpose basically. So you will get like 2 ones that will be added. So that will give you 2. And that 2 ones will be added means that represents a degree. So this diagonal entry will come degree. Similarly, this row, when it will be like you will take the inner product with itself. So that will give the 2 entry in the product, and that will again give the degree. So all the diagonal entries, they will come as degrees. And for off diagonal entries, basically you are multiplying a like one row with another row. So if you see, like when I'm taking the first row and then second row, if I multiply, they will give me a -1 if they both correspond to one edge. So they are end vertices of one edge. Then you will get a 1 and a -1. Otherwise, you will get a 1 and 0 or 0, -1 or 0, 0, that kind of thing. So if both the rows, they correspond to 2 vertices and they are adjacent, then you will get like 1, 1 and corresponding one is -1. So that will, the inner product will give you -1. So that means when they are adjacent, basically -1 will come. So if you take Q and Q transpose, then this way it's giving you nothing but the Laplacian matrix. So Laplacian matrix can be expressed in this way, the incidence matrix, using incidence matrix. But when I define the incidence matrix, I took the oriented graph, means directed graph. So I put one orientation, but that's not fixed. You can take any arbitrary orientation. As you observe, that's going for Laplacian matrix, and that is defined for simple graph without directions. So any orientation you put, you will get the same matrix. So this orientation doesn't matter. You can put any arbitrary orientation and define your Q. So what do we observe? L is Q into Q transform, and that tells that the matrix is positive semi-definite. So LG will be positive semi-definite. You know this, right? Any matrix, if you express in this way, some A into A transpose, then obviously that matrix will be positive semi-definite, because you can take like X transpose LGX, that will be X transpose Q transpose X, and then that is looking like X into X transpose for some vector. Like if I assume that X transpose Q is some X, then it will look like X into X transpose, and that will be always non-negative. So from this, we can observe that it's a positive semi-definite matrix LG. And that can be proved in other way also, we'll see. But this way, it's like it's coming. Another thing, as I told, like for Q, all the column sums are 0, but for Laplacian, if you see, all the row sums are 0, because you are taking the diagonal as degree, and then how many minus ones are coming, those are basically to how many vertices one is adjacent. Like if you look at first row, this is the degree, and if I am getting 2 minus 1, that basically giving like how many vertices it's adjacent, those are coming as -1. So if I add them, all the row sums are 0, and the matrix is symmetric, so all column sums are also 0. So since all row sums are 0, we can say that 0 is one eigenvalue, and the corresponding eigenvector will be the all ones vector. So that's coming from this. So one thing is LG positive semi-definite, and the second thing is 0 is one eigenvalue. So because it's positive semi-definite, all its eigenvalues will be greater than equal to 0. And one eigenvalue is coming as 0. Maybe 0 will appear again, but we know that the smallest one will be 0. Now, I define Q because in terms of Q, we can say many things about the Laplacian LG. So first interesting result is if the graph G is connected and with n vertices, then the rank of Q will be n-1 exactly. So that can be proved easily, like the way you means I define the matrix, and if you observe the matrix, you can prove it. So here I am giving the outline. So suppose that X is because you observe that Q is not a square matrix; it's a n cross m matrix if m number of edges are there. So I'm taking a eigenvector that is a left eigenvector I'll consider. So basically I'm looking for the null space of QZ, but the left null space. Okay, so let us start with a vector X, and that is, let's say, lying in the left null space of QG. Then I'm just taking the example that we had taken. So I'll consider this expression that let's say X transpose QG I'm considering. So X transpose QZ, if I multiply, you can observe that when there is a 1 and -1, because it's getting multiplied to the columns. So if you see like 1 and -1 appeared for this edge E1, because E1 was adjacent incident with like vertex 1 and vertex 2. So this was the starting vertex and this was the ending vertex. So then when I'll multiply, I'll get x1 minus x2 there. Similarly, in this column, which are the end vertices corresponding to that, I'll get one expression like this, x1 minus x3. And when I'm looking for this is in the left null space, this vector. So basically this quantity will be 0. So then these will be all 0. So you can observe that x1 will be equal to x2, x1 will be equal to x3 like this. So if a vector is lying in the left null space, then the corresponding entries like x1 and x2, they are equal to 0 if one is adjacent to 2. Similarly, 1 is adjacent to 3, then x1 will be equal to x3. It's like this. So this way it's happening. So if your I is adjacent to j, in general, if you see, then xi will be equal to xj. And if I have a path like from I to j, then I can proceed accordingly, like x1 will be equal to x2, x2 will be equal to x3, like this. So if there is a path between I and j, xi will be equal to xj. And we have taken a connected graph. So this way I can prove that, because in connected graph, every two vertices are joined by a path. So you can prove that x1 is equal to x2 equal to xn. So all the entries will be same. That means if I'm starting with a vector, any vector in the left null space, that is coming as the vector where all the entries are same. So basically the left null space is with the vector, all one's vector, and that's the basis for it. So that tells that if you are looking for the rank of QG, because null space is becoming one-dimensional, so rank of QG will be greater than equal to n minus 1. Okay, but what we observed is like if I add all like column entries, that means column sums are 0. So basically, if I look at the rows, they are dependent. So in the matrix, because all the rows are dependent and it has n rows, so I can say that the rank of QG must be less than equal to n minus 1. So using both, you can conclude that rank is n minus 1. So if G is a connected graph, then rank of Q is exactly n minus 1. And not only that, if you are taking a disconnected graph, and then let's say it has k components, then rank of Q will be exactly n minus k. And that can be observed easily, because when the graph is disconnected, you can write it in this form, because if you have like G1 to Gk, let's say the connected components, then you can express your Q in this way, in diagonal form. And then rank of this obviously is equal to rank of QG1, rank of QG2, like this. And for all these, because they are connected components, so here if there are n1 vertices, you can say that the rank of QG1 is n1 minus 1, like this. So if you add, you will get n minus k. So if your graph is disconnected with k components, then the rank will be n minus k. Now another nice thing happens in QZ, that is QZ is totally unimodular. That means if you take any square submatrix of QZ, then its determinant will be 0 or plus 1 or minus 1. So it's means QZ is totally unimodular. So QZ may not be square, but if you take any square submatrix of any size, then this happens. The determinant will be 0 or plus minus 1. And to prove this, you can use induction. So induction will be used on the size of the submatrix. So with submatrix you are choosing, its size there will put the induction. So let's say we're taking K, it means the size or order of the submatrix. So if I take k equal to 1, the statement holds, because if I take k equal to 1, then already we have observed Q has the entries as 0 or plus 1 or minus 1. So if I'm taking any submatrix of size 1, then it will be 0 or plus 1 or minus 1. That's clear. Now, if you assume the statement hold for k minus 1, and let us take a submatrix of order k. Okay, so B is a submatrix of order k, and we want to show that the statement holds for B. Okay, and we are assuming that for k minus 1, as means order k minus 1, the statement holds. So if I look at B, and if each column of B has a plus 1 or minus 1, and a minus 1. So every column, if the submatrix I have chosen, let's say it has every column with a plus 1 and a minus 1. In that case, obviously, then column sums are 0. So basically, the rows are dependent. So you will get determinant of B equal to 0. Okay. So in that case, it's giving you 0. Similarly, if B has a 0 column, then also determinant of B will be 0. So if these two cases are not happening, means all columns are not with plus 1 and minus 1, or there is no 0 column, and then you have the option that you have at least one column which contains only one non-zero entry. That may be plus 1 or minus 1. So in that case, what you will do when you will calculate the determinant, just expand the determinant corresponding to that entry. So then you will get plus 1 into a submatrix and determinant of a submatrix which is of size k minus 1. So then, or minus 1 into determinant of a matrix which is of size k minus 1. So then you apply induction on that matrix and you will get that determinant will be plus 1 or minus 1, 0. So accordingly, you will get the determinant of B is plus 1, minus 1 or 0. So using induction hypothesis, you can prove. So you have to expand, if there is such a column, you have to expand the matrix corresponding to that entry. So then it will be done. So what we got is QZ is totally unimodular. So this I'll use in the next result and also in matrix theory. So here this is a interesting reason that if you are taking a tree, then any submatrix if you are choosing of size n minus 1, that means if you are taking a tree, obviously you have n minus 1 edges. So your matrix is n cross n minus 1. Now, if you are choosing any submatrix, which is a square submatrix of order n minus 1, that means basically you have n minus 1 columns. And from rows, n rows, you are choosing n minus 1 rows. So that way, if you are choosing a matrix, that will be non-singular, means determinant will be plus 1 or minus 1. So to prove this, let us take a submatrix Q of Q, and that I'm forming using the rows corresponding to the vertices 1, 2, and n minus 1. So first n minus 1 rows you are choosing, and all the columns are chosen because you are taking a n minus 1 order matrix. So you have only n minus 1 columns because it's a tree. So if we are choosing first n minus 1 rows and making the matrix, that is I'm denoting by X. Okay, now if I add all the rows of X, okay, then what I'll get, like, let us add all the rows of X to the last row. Okay, so what you will get, that will be obviously negative of the last row of QG, because QG has column sums equal to 0. All the column sums are equal to 0. So if I add all the rows and all the rows, so it was giving me 0. So if I'm adding the first n minus 1 rows and making the last row of your X, then that will be nothing but negative of the last row of Qs, right? So like in this example, you can see, so this is a tree and I have the QG. So if I take this sum matrix, this is my X. And now if I add the like this row, this row, this row, and make replace the third row by addition of all these rows. If I add all these rows, what you will get, like 1 minus 1, and that is 0, and that's same as your last row of QG. So similarly, you can see other entries. So if I add all, because in QG, actually, if we are adding all the rows, that was giving us 0. So if we are leaving some row and then adding all other rows, obviously that will become the negative of the last row. So this way it happens. So then if I denote Y is the submatrix of QZ, that is formed by taking the rows 1 to n minus 2 and the last row n. So I'm leaving n minus 1. Then I can say that determinant of X will be determinant of Y, because what we did is we just added the rows and made the last row of your X. So that will not change the determinant. So whatever the determinant will come, that will be same as the determinant of Y if I take this rows, okay, and form the Y. So this tells that if determinant of X will be 0, then determinant of Y will be 0. And similar way, I can change, like here I consider the first n minus 1 rows, and then I went for leaving the last row. But this interchange I can do with any row. So what I can prove that, like if the determinant of X is 0, then each n minus 1 cross n minus 1 submatrix of QZ if I consider, their determinant will be 0 also. So if any one of the n-1 cross n-1 submatrix of Q will be with determinant 0, then every one, like any one you are choosing, that will be also 0. So one submatrix becomes singular, that means all will become singular. So, but that's not true, because a rank of Qs is n-1. So at least one of the n-1 cross n-1 submatrix must be non-singular. So that means like determinant x and determinant x of x also not 0. And every submatrix is like with determinant non-zero. So this is the proof that if you are taking any submatrix of size n-1, then determinant cannot be 0. So it will be +1 or -1. So you got it, or I can repeat? Okay, so for a tree, if you are given with a tree on n matrices, then any submatrix of QZ of size n-1 must be non-singular. Now, what we observed for Laplacian matrix, like I can conclude using our QZ. So first thing we observed that LG must be symmetric and positive semi-definite. That was coming using QG, and that will also can be concluded if we can prove this one. So LG is symmetric. That's by definition positive semi-definite, because it can be written as Q transpose. And now I can also say that if G has K connected component, then rank of LG is n-K. And if it's connected, then rank of LG will be n-1. This can be concluded because LG is QG into QG transpose. And for QG, we have observed this, that if G has K components, rank of QG will be n-1. So rank of LG is nothing but rank of QG, so that will be again n-1. Third thing is this one, that if I take X transpose LGX, that will look like this, that it will be a sum of xi minus xa whole square, where I is adjacent to j. So looking at how many edges, those many terms will come. This expression we'll discuss. And this also makes that, tells that LG is positive semi-definite. And the row and column sums of LG are 0. This we have already observed, that because diagonal entries are degrees and off diagonal entries are -1 if the corresponding vertices are adjacent. So this gives you the row sums, column sums are 0. And the cofactors of any two elements of LG will be equal. So this I'll prove, and this I'll prove. So we'll see other things we already know. So to prove that this third part, this one, that if I take X transpose LGX, and that will take this form. So I'll go through, I'll take one example, and then I'll show you how the things are happening. So the matrix I'm taking, that is the matrix which we had taken before, that is from that graph coming, and that is, I had taken the graph and that example. So if I take X transpose LGX, okay, so just take any vector X, so X1, X2, X3, X4. So I look for this expression. I have to write it as a sum of squares. And just multiply in the way you want to multiply. So you will get your entries, and finally you will get like this. But if you observe here, you got this 2x1 square, because here the corresponding to the first row, if you see this degree is 2, so 2x1 square will come. Similarly, 2x2 square will come, 3x3 square will come. And if I look at these entries also, they are basically when there is one edge, actually they are coming, like x1, x2 is coming because 1, 2 are adjacent. That way those terms are coming. And if you put them together, like I can write them like this. So I took 2x1 squares were there. I took 1. So x1 square, and I put together two x1, x2, and this will look like this. And that's coming because 1 and 2 are adjacent. So you will get this way, like 1 x1 square will come, x2 square will come, and then minus 2 x1, x2. Similarly, because you have one edge between 1 and 3, I'll get this thing. Okay, and that's coming from your multiplication directly, you can see. And your 2 and 3, they are adjacent, you will get this kind of thing. And 3 and 4, they are adjacent, you will get 1. Okay, and finally, so you can express them as squares. So when there is one edge, like between two vertices, you will get one expression like this. So 1, 2 are adjacent, then x1 minus x2 whole square will come. Similarly, how many edges are there? Those many terms will come, and all are square. So you can express your this x transpose LGX as a summation of this is over all adjacent vertices. That means I is adjacent to j. Then you will get the term xi minus xa whole square. Okay, so this way also you can say that this LG is positive semi-definite matrix. But this is a nice thing that this multiplication, what it will come, you can just looking at how many edges you can write this as what. Now, the fifth part of the theorem is all the cofactors, they're equal. So basically, if you consider any two cofactors, so they will be equal. That we can show. So as we observed that LG is with row and column sums 0. So for cofactor, I'm denoting like obviously you have to take minus 1 to the power I plus j and determinant of this. So this is the sum matrix obtained by deleting the row I and column j of L. So that I'm denoting by Lij. Okay, so cofactor of ij, that will be minus 1 to the power I plus j, determinant of Lij. Okay, so we'll look for first determinant of L11. So this is the cofactor of 1, 1 and 3. So determinant of L11 when I'm looking for, so basically I'm deleting first row and first column to make L11. So your matrix will be this. And we're looking for the determinant. So what I'll do, I'll add all the rows and all the columns to the first column. So that will be replaced by the first column. So you will get this. And as we did earlier also, you can observe here because all the rows, all the column sums were 0 and all the row sums are 0. So here when I'm doing this, if I add here L11, then that will make me the first row sum, and that's 0. No, sorry, L21. So if I add here L21 and this expression, total will be 0 because the row sums are 0 for LG. So this can be replaced by minus L21. Similarly, this can be replaced by minus L31. And this can be replaced by minus Ln1. So this determinant is same as this. And this is same as if I take the determinant of L12, that means the second, here you can see the second column is missing and the first row is missing. So this is nothing but just minus 1s are here, which will come as minus 1 to the power 1 plus 2. So that will give me this, here I think. So this will give me here minus 1 to the power, I left it. So this will give me the cofactor of 1, 2, and 3. So if you look for cofactor of 1, 1, and 3, that is same as cofactor of 1, 2, and 3. Similarly, we can prove like I added to first column, you can add to any column and you can show that the determinant of L11 is same as, or the cofactor of L11 is same as cofactor for L1j for any j. Okay. And similarly, I can go for also the matrix is symmetric, so I can show in the other way that cofactor of Lij is equal to cofactor of Lik for any ijk. So all the cofactors, they are equal. This result can be true also for any matrix which has row sums, column sums equal to 0. So you can show that the cofactors are all equal, and nicely LG satisfies that. So LG has all the cofactors there with equal value. Okay, and if I look at the cofactors, they are determinant of like some matrix of LG, and LG is an integer matrix. So if I'm calculating the cofactor, that will give me some integer. Okay, and all the cofactors they are same, we know, but that will come out as some integer. Now, if I look at the other eigenvalues, and as I told, because 0 is the smallest one, if the graph is connected, then this will be the only 0 here, and others will be positive. So that we have already discussed. So this was proved by, means this was observed by Fiedler, that the second smallest one that will be positive if and only if the graph is connected. And that happens because we already discussed that rank will be n minus 1 if and only if the graph is connected. So this comes naturally. All other eigenvalues, so if the graph is connected, so all other eigenvalues will be positive and you will get a 0 eigenvalue. Okay. So on this eigenvalue, because it's deciding the connectivity, not only by this result, but also we can observe in other way also. So this is known as the algebraic connectivity of the graph. And the corresponding eigenvectors, it can have multiplicity more than one. So the corresponding eigenvectors, those are known as the Fiedler vectors. So the second smallest eigenvalue that from now onwards, I'll say that this is algebraic connectivity. And this decides as it's positive, then the graph is connected. This is the, not only this is true, how much like bigger this lambda 2 is, that also decides how much the graph is connected. Like if you see complete graph, so the Laplacian eigenvalues for the complete graph, I hope you know, otherwise you can compute. So those will be 0, and n will appear n minus 1 times. So in the Laplacian case, so Laplacian eigenvalues will be 0. That's coming obviously once, and then all others are n. So in that case, you can see algebraic connectivity is n. And that is the graph which is highly connected because the largest algebraic connectivity. And similarly, like you can see, like I'll give example later. So like in the path, it's the smallest one. So path is it's a tree. So it's having the less number of edges, like n minus 1. Also, it's path is with full diameter. So it's less connected. Any edge you are deleting, it's becoming, any tree is even you can consider. For tree, the algebraic connectivity is less than equal to 1. So, and when you are putting more edges, the algebraic connectivity increases. So it decides the connectivity and also how much it is connected. So that way its name is algebraic connectivity. This eigenvalue, I'll maybe in the second lecture, I'll tell about this eigenvalues and its corresponding vectors. So these are Fiedler vectors. They are also related to graph structure. Obviously, as you know, adjacency matrix is the first matrix that expresses the graph in terms of matrix, and that was a natural one. Laplacian matrix came later, but if you see the results and the observations, Laplacian matrix is more natural in the sense that it tells much about how the graph structure is. So how the graph behaves, you can conclude looking at the algebraic connectivity and other eigenvalues and the Fiedler vectors. Fiedler vectors are much more important these days due to application. So I'll say the application may be in the next class, but just I want to say that these are very much related to graph structure. Now, like the matrix T theorem, so that came, I think, in 1847. So that was proved in another way. And at the time, I think the spectral graph theory part came later. And which proof I'll give here, these are I can say different proofs or like alternate proofs. But this is the first result that uh, how many distinct level trees are there on n vertices. So you are taking a tree on n vertices, and then how many trees I can form, and those I have to label also. The vertex should be numbered. So this is a vertex we are numbering, and this labeling is important because graphs can be related to many things, and sometimes your vertices are different in the sense of practical use. So here we are considering how many label trees are there on n vertices. Okay, and that was proved by Kelly that there will be n to the power n minus 2 distinct label trees on n vertices. And that if I write in other way, so how many spanning trees of Kn are there? And that is exactly equal to n to the power n minus 2. This is so many proofs. I think for Kelly theorem, there are at least 15 proofs are there. But all the proofs are difficult in the sense the easiest one is also difficult, like which I teach in the class. So that is also using functions, but that's also difficult. But this Kirchhoff matrix theorem, that is a more general one that tells that, like here we're looking like all the label trees on n vertices. So basically we are looking for spanning trees for Kn. So in the proofs we can use counting, and in combinatorial way we can just do the counting. But if I start with any graph, so G is a graph on n vertices. Okay. Now, if I want to know the number of spanning trees, it's difficult. If you go for like this counting, this can be, as I told, this can be proved in many ways. But if I start with any graph, how many spanning trees are there? That's a difficult task, like the way they were calculating using algorithm, and that takes time also. But this result gives that if you just look for the cofactor of any element of LG, because for any element, if you are taking the cofactor, that giving the same value as we observed. So then the cofactor of any element will give you exactly the numbers of spanning trees of G. So using this Kelly theorem can come as a corollary, but we'll look for the proof of this. And nicely, this theorem is telling much more, that if you are like if you know the eigenvalues, Laplacian eigenvalues of the graph, then the number of spanning trees is equal to, like, just take the non-zero eigenvalues. Obviously, your graph should be connected, otherwise you will not get a spanning tree. This quantity will become zero in that case. And if your graph is connected, then obviously lambda 2 to lambda n, they are positive numbers. So you just multiply them and divide by n. That will give you exactly the number of spanning tree. So by number of spanning tree, like as I told, those should be labeled. So how I'm counting that, I'll tell you through one example. Like this is the graph, let's say. So when I look for the spanning trees, so I'll also consider my vertex labeling. So when I'm taking like this is one, so here you can observe there are 5 edges are there, and graph has 4 vertices. So my tree should contain 3 edges. So I'll delete 2 edges mainly from the graphs to make a tree. And this is one tree. I deleted the 1, 2 edge and 3, 4 edge. And this is one tree which I deleted 1, 4 edge and 2, 3 edge. So both I am counting because I'm giving the labeling as like importance. So this you can say that this is the path of order 4. This is also path of order 4, but its starting vertex is 4 here, and then in between, like sorry, I think here 1 to 2 are connected. Here 1 to 2 are not connected, means not adjacent, like this. So this is different from this, considering labeling. Otherwise, if you don't take labeling, then both will be counted once. So here, when we're counting number of spanning trees, we are considering labeling also. So this is a tree, this is a tree. And similarly, if I go for, like, I deleted middle edge and then the below one, and the middle edge and the above one. So this will give again paths, but this as per labeling, those are different also. So these are again another 2. And then I can delete the middle one with this side and that side. This will give another 2. And I can delete also like 2 from side and keeping the middle one. So this will create stars. So these are 2. So there are exactly 8 spanning trees. And that can be computed because this graph has, if you calculate, this graph has spectrum, Laplacian spectrum 0, 2, 4, 4. Okay, these are the eigenvalues. So if I take the non-zero eigenvalues and make the product, that will give me exactly 8. So this result is a crucial result that tells exactly the number of spanning trees for any graph. Okay, so we'll go for a proof. One part already I have shown that any cofactor, if you are taking that value is equal value, means you are getting a unique value for any cofactor. So now we'll calculate what is the value is coming, and we'll show that that is the number of spanning trees. Okay, so if I calculate this cofactor, let's say I'm taking the cofactor for 1, 1 entry. So L11 and its determinant will compute. So L is expressed in terms of Q and Q transpose. So Q transpose I'll put in place of L. So then now here, because this is a matrix which is not square, this is a rectangular matrix and its transpose we are taking. So in this way it has been written. Then here I'll use the Cauchy-Binet formula. Okay. So Cauchy-Binet formula, through this example, I'll tell how it gets applied. So if you have 2 rectangular matrices and order is in this way matching so that the product can be possible. So here it's like 2 cross 3, then this should be 3 cross 2. Okay. So like this way, then determinant of AB, because this is, I cannot make like determinant of A into determinant of B because these are rectangular matrices. So determinant of AB is a square matrix. Then that can be computed, just take, because this has 3 columns but 2 rows. So all 2 cross 2 sum matrices you have to take. So like I deleted this one, this is the sum matrix from A. Then accordingly here also you delete, like here I deleted the 3rd column, here you delete the 3rd row and the corresponding sum matrix you take. So then you take the determinant of this. Okay, so I forgot to put the bracket. So determinant of this into this. Similarly, you can delete this column here. Here also you delete this column and then take both the matrices. So determinant of this product. And similarly, you can do the first one, you can delete here, and the first row you delete here, both the matrices you take and the product, determinant of this. So this way, like determinant of AB can be written in this way. That is the Cauchy-Binet formula. So here I'll use the same. Your Q is N cross M. Okay. So, and when you are taking like a sum matrix here, L11, so you have already deleted your first row and first column. So this Q into Q transpose L11, that has N rows, right? So I'll take the N rows and then you have to choose n minus 1 rows, sorry. N minus 1 rows are there because you have deleted your first row, first column. So n minus 1 rows I'll choose. And from your columns can be more. So you will choose n minus 1 columns. Okay. And then you will multiply with Q transpose that thing also. So, but when you are taking determinant, so Q of that and Q transpose of like this matrix that have same determinant, so this term will come as square. So this will be sum is like over all Z, and Z mod you are taking n minus 1. So basically you are taking n minus 1 column. So this way you have written it as a sum, and because the product will give you squares. So you will get that how many such determinants are coming and which are non-zero, that will contribute. And this is a sum matrix of Q, you can observe. So that has determinant +1 or -1 or 0. So its square will be +1 or 0. So how many such non-zeros determinants are coming, that is basically this quantity determinant of L11. That is cofactor of L11 that we are going to count. Now, if I look for such determinant, that is a submatrix we are taking with n-1 rows and corresponding n-1 columns, then you can observe that, because I had already proved that if you are taking a tree, then corresponding Q, if I am considering, then if I take any n-1 submatrix of that, that will be non-singular. And that happens in the other way also. That will be non-singular only when that is tree. And that I'll leave as a homework. You can observe that if I'm taking a submatrix of n-1 size for any graph, for tree we have already proved. If we are taking a tree, then if I'm taking n-1 size square submatrix of Q, that will give you +1 or -1. And if I am taking a graph, and let's say the corresponding submatrix contains a cycle, you can observe that the determinant will be 0. So this you use here. So then your sum, this sum, will contribute +1 when this submatrix corresponds to a tree. Okay. Otherwise, this will give you 0. So you are choosing all the submatrices of size n-1, choosing your columns, but this will contribute 1 only when this corresponds to a tree. So that gives you that the sum basically gives you the how many spanning trees are there. So this is the proof, but you have to take a graph and see. And basically one part I have already shown, that if you are taking Q and Q is corresponding to a tree, we have already shown that any submatrix of size n-1 has determinant +1 or -1. The other thing is, if you have to observe that if it's not a tree, that means some cycle is there. And then you can observe that your columns will be dependent. So that way you can show that that will contribute 0. So this sum actually gives how many +1s will come, that will depend on how many spanning trees are there. So this sum will give you the number of spanning trees of the graph. So this is the proof. Then, as I told, this is more interesting, because if I know somehow the eigenvalues only, and then I can get the number of spanning trees. And this can be easily proved, because what you know is you are calculating this through, you have already proved that this is the number of spanning trees is nothing but equal to the cofactor of the Laplacian matrix, any cofactor. And if you recall, if I look for the sum of the principal submatrices of LG of of order n-1, that is same as sum of the products of eigenvalues taken n-1 at a time, right? So this way you write, right? This comes from if you look at the characteristic polynomial. So determinant of L11, that is the principal submatrix deleting the first row and first column. And then if I add with the second one, that is deleting second row and second column. That means I'm taking all the principal submatrices of size n-1 and then adding. That is same as you take the eigenvalues products n-1 at a time, all possible. So that you will get whatever the sum, this sum is equal to this. This happens for any matrix, okay? And you can take size 1 cross 1, here you will get lambda 1 plus lambda 2 plus lambda, and that is, this side will be trace and this side is sum of the eigenvalues. Similarly, you can take 2 cross 2 also, that will give all possible two products of eigenvalues. That is true for any matrix. So here for Laplacian matrix, we are taking the all n-1 cross n-1 principal sum matrices. And if I take the minus, that means the determinants, and add them, that will be same as all possible products of eigenvalues taking n-1 at a time. But if you observe, your lambda 1 is 0. So all these terms except this one, which is starting from lambda 2 to lambda n, all these will be 0. So in this side, all these determinants are equal, that you know. And in the right side, you will get that only one term is there, that is lambda 2 to lambda n. So you will get that n times number of spanning trees is this. And from this, you are getting this. So this is about the matrix T theorem, and this part is interesting. And this, I think, came later. So now there is also a generalization of matrix T theorem. Like matrix T theorem, in matrix T theorem, you are looking at like here the term you are calculating, this is the cofactor that has n minus 1 into n minus 1, this sum matrix. And this denominator is that one basically, and that's giving you this, okay? But for any sum matrix also you can get a value accordingly. And so basically it relates to the coefficients of the characteristic polynomial, as I told. So this is a more general like result that was by Kelman. So this gives the combinatorial like interpretation of the coefficients of the characteristic polynomial of LG. Okay, in terms of some number of certain subforest of the graph. So here you may not get spanning trees, but spanning like subforest, you can say, or forest, that way. So this result is like if phi LGX, this is the characteristic polynomial. If that you are taking like this, first term it's a monic polynomial, so x to the power n, and the last term will be 0 because determinant is 0. So I'm ending here up to x. Now these coefficients you can also calculate looking at the like spanning trees for the subgraphs. So that's nice. It's not happening in like in adjacency case also similar kind of result is there, but there we use linear subgraph. Here if I want to count ci will be minus 1 to the power I, and this summation is you have to take a subset of Vg, and such that if you are counting I like ci, then you will take a subset of Vg which is of size n minus I, and now you look for spanning trees of GS. GS is a graph which is obtained from G by identifying all vertices of S to a single vertex. So you chose your S of size n minus I. Now all the vertices of S you just make one vertex. Okay, so that way you made the graph. That is your GS. So now look for all the spanning trees in GS. Okay, and then this will be the term, and make like take all possible S's, and then this sum will be calculated. This will give you your CI. So this is one way you can just count the like C1 to Cn minus 1. But you can also observe that C1 to Cn minus 1, when you are counting, basically you are taking the principal sum matrices of that size and that. So those sum of the principal sum matrices actually equal to this quantity. So this is, I am not going for proof, but this is one interesting result. I think this is also like 1965 or something, this result. Okay. Now, for you, I'll give these two problems to do at home. So this is another expression for the number of spanning trees. So G is a graph with n vertices. Then you can get also the number of spanning trees will be 1 by n square, determinant of L plus J, where J is the matrix of all ones. So on this problem I'll ask you to do. And similarly, another problem that this is also giving a bound for the number of spanning trees. That number of spanning trees bounded by this. This expression is in terms of n and m. M is the number of edges. So this is also a bound. So these two questions I'm asking, you can solve. And some related problems that I want to say here. One of the interesting problem that is going on now, and that is the Brouwer's conjecture. That if you are looking for all the eigenvalues, so here I have changed the ordering because I want to express in a nice way. So let's say lambda 1 is bigger and lambda n is the smaller one. Then lambda n is 0, that we know. And let us define this sum. This is sum of the largest k eigenvalues. Okay. So if I'm taking skg, then it's the sum of the largest k eigenvalues. So S1g basically lambda 1. S2g is lambda 1 plus lambda 2, that is the largest two eigenvalues. Like this, it's defined. And the conjugate degrees, like when you know that the degrees are d1, d2, dn, conjugate degrees are defined like this. dk star is how many vertices have a degrees greater than equal to k. Okay, so that is the conjugate degree of dk. Like for example, here this is the graph. Then you have the degrees like d1 is 2, d2 is 2, and d3 is 3, d4 is 1. So if I look for d1 star, that means I'm looking for how many degrees are greater than equal to 1. So those will be 4. So d1 star is 4. d2 star is how many degrees are greater than equal to 2. So that will give me 3. And d3 star is how many degrees greater than equal to 3. That is 1. And d4 star will come as 0 because there is no degree greater than equal to 4. Similarly, other values, they will come as 0. So it goes up to finite terms, and after that it becomes 0. So if I take all these numbers, this is called as conjugate degree sequence. And this is called the degree sequence. Okay. So this was the Groen-Meris conjecture. They had given that the sum of this k largest eigenvalue skg, that it will be less than equal to sum of like k degree conjugate degrees. And this was proved by Bai. So now it's known as Groen-Meris Bai theorem. It's no more a conjecture. It was proved in 2011. Now, after this, actually, this Brouwer gave another conjecture that is a more tight bound, that is skg will be less than equal to the number of edges plus k plus 1 c2. Okay, so this is the bound, and this conjecture is still open, and sometimes it seems like very difficult in certain cases because this bound becomes tight bound for certain classes. So this has been developed in the sense that few results, like for few k, it has been proved. Like when I'll take k equal to 1, obviously skg is only lambda 1. So lambda 1 is less than equal to n. So that way you can prove easily that lambda 1 less than equal to n. So S1g will be less than equal to this quantity for a connected graph. For a connected graph, this will be at least n minus 1, and from here you will get to 1. So for k equal to 1, this is true. Now for if I take k equal to n minus 1 or n, then also because sum of all eigenvalues is same as sum of the degrees, and that is 2 times number of edges. So this will satisfy this, and your conjecture means that conjecture is true for k equal to n and n minus 1. And Hammer, he proved that for k equal to 2, the conjecture holds. That means if I take lambda 1 plus lambda 2, the largest two eigenvalues, then we can show the conjecture is true. And this is a more this is like what I can say, that's the more important result to develop the conjecture, in the sense that it's telling much more, that it's saying that if the conjecture holds for certain k, which is let's say p, and p is lying between 1 to n minus 1 by 2. So for some p, if it holds, then it will hold for k equal to n minus p minus 1. Okay. So if you can show the conjecture holds for these numbers, which are lying between 1 to n minus 1 minus 2, then the conjecture is proved. So using this one, now we can, because it's true for n minus 1, now 1 and 2, we can say that it's true for n minus 2 and n minus 3. So up to this, it has been done in terms of the k value, but it has been also proved in many classes. Like for trees, the conjecture holds. That has been proved by Hammer. And for threshold graphs, the conjecture is true. So that is also proved by Hammer. For unicyclic graph, bicyclic graphs, the du and Jo, they have shown that it's true. For regular graphs and split graphs, Moyank has shown in his thesis that it's true. So there are other classes also, like for if two graphs it holds, then it's for its Cartesian product also it holds. Those kind of work has been done, but the conjecture is still open, and for general, like 1 to n minus 1 by 2, it has not been shown for all case. So it's a very interesting conjecture, but like sometimes like we feel it's very difficult also. So the students who are here, they can try also. This can be tried in many ways, considering several classes, or it can be considered in terms of K, but it's a nice problem. So for this talk, I used the book by R.B. Bapu. So whatever proofs or certain things I missed, you can go through. And I also followed this book by Brower. And obviously, this is a classical book, but this contains everything we use as definitions or anything. So this book is students can follow this book also. So these three books I consider for this talk. Okay, so I'd end here. Any questions you can ask?
Okay. Stop recording first. Yeah.